Okay, so we're going to actually now go in, dive in, and do an actual exercise in which we have three groups and we want to compare the means. Okay, normally we'd have to, if I'm going to open it up and show you in Excel what the group look like, what the groups look like. Let me just get to it. Let's try this one. I think that one's more likely. Oops, don't need it right now. Okay, so we have three groups. These three groups are named Fred, Jim, and Alice. This might be, maybe this is the average number of work shifts that they, average number of patients that they dealt with. Maybe it's in a hospital setting, or the average number of clients that they saw in a week or something like that. Whatever it is, I'm not really going to bother with a backstory for this. But we have three groups: Group A, Group B, Group C. If we wanted to compare these and prove that the average for Fred is different from the average for Jim, is different from the average for Alice, we were going to use a t-test. First, we'd have to do the t-test, compare Fred and Jim. Then we'd have to do the t-test to compare Fred and Alice. Then we'd have to do the t-test again to compare Fred, Jim, and Alice. So we do it three times. That triples the likelihood that we're going to reject the null hypothesis when we shouldn't. Okay, it increases our chances of being wrong. So we're going to calculate this F statistic that we've just looked at. First thing we need to know is we need to know the variables within the groups, that variance within the groups, the variability within the groups, and we need to know the variability between the means of these groups. So I'm going to start with the variability within the groups. Here's the group Fred. Okay, first thing I need to know to calculate the variability, you may remember this from when we started the semester. I'm going to find the average for Fred, and I'm going to find the average for Jim, and I'm going to find the average for Alice. Okay, so 1.8, 3.44, looks like a big difference between Alice and Fred. Not so big a difference between Fred and Alan, not that much difference between Jim and Alice, and so on and so forth. We got mixed results here. But now let's see what we have to do to calculate the variability within the group. Well, first thing I'm going to do is I'm going to put this mean next to each one of these. So this is going to be equal to X bar, or the mean, is equal to 1.8. In order to help my calculations out, I'm going to put a $sign in front of each one of these so I can copy it down without changing its position. Okay, just like that. And I'm going to copy this down. Okay, I'm going to do the same thing here. In other words, I'm using absolute addressing rather than relative addressing. So I can get that 3.4 to copy down. I could also just type in that 3.4, type in that number if I wanted to. But this, I can do it this way, and it's less likely to make an error since I don't have to transpose or round or do anything like that. And I'll copy this down. Okay, now I'm going to find the difference between each one of these means and the value. I'll do it this way. Just to be consistent, I'm going to say it's X bar minus X. Well, actually, I'll do it the other way. So I'll keep the column straight. X minus X bar. And I'm going to fill down. And I'm going to do the same thing here. X minus X bar. And I'm going to copy that down. And I'm going to go here. X minus the mean of this group. Find all the differences between the means in each individual value. Okay, then I'm going to take the square of the differences. And I'll copy that to square it down. Same thing here. And I'm going to copy that down. Okay, and finally I'm going to take this one, square each one of those differences, and I'll copy that down. Okay, and then I'm going to take the total of all of these. And you guys remember what that's called? Actually, it's not such a hard question since I typed it right next to it, right? You recall that that's called the sum of the squares of the differences, or the sum of the squares. Yeah, you guys recall that, right? Any questions so far? There's nothing here that we haven't done before. Am I correct? Okay, let me just get a response so I know you guys are still there. Okay, good. Okay, no surprises, right? So now we're going to take these sums of squares and we are going to use them to calculate the variance for each one of these groups. Okay, so now let's see. Sum of the squares of the differences within the groups. Well, that's each one of these values is the sum of the squares within the group. So it's sum of the squares here plus the sum of the squares here plus the sum of the squares here is the sum of all the squares within the groups. Well, now I want to get an average of that, the mean sum of squares within the groups. Well, in order to do that, just like I calculate the variance, I'm going to divide by the degrees of freedom, or the sample size minus 1. In this case, the sample size is 15. There's 3 groups, so it's going to be 15 minus 3. It's going to be 12. The degrees of freedom is going to be 12. And I'm going to take my sum of squares of the differences within the groups and divide it by my degrees of freedom to get that variability. That's equal to 2.1. Well, you might remember that the F statistic is equal to the sum of the squares between the means divided by the mean sum of squares within the groups. Well, the mean sum of squares is what we just calculated. That's our 2.1. Okay, now I'm going to do the second part of this is that I'm going to go ahead and calculate the mean sum of squares between the mean sum of squares between the groups, between the means. Okay, well, let's see how I'm going to calculate that. Well, first of all, the overall mean for the 3 groups is equal to the mean for the first group plus the mean for the second group plus the mean for the third group. Now, they happen to be all the same size, right? Divided by 3. I'm going to put a parentheses around here to make sure it does these calculations correctly. Okay, and the overall mean is 3.2. I'm going to copy this down. I'm going to type it in rather than do it any other way because I just need 2 copies of it. And I don't need it comes out to be a nice even number, so I'm not rounding unnecessarily. Okay, so what are the means of each group? I'm going to find the variability between the individual means and this overall mean. Okay, so the variability within the means themselves. I'm going to do the same thing, except I'm doing it for the 3 numbers that represent the means of these 3 groups. Okay, so the means of the first group, mean of the first group is equal to 2.8. Mean of the second group is equal to 5.2. The mean of the third group is equal to, where is it? Is equal to, oops, I made a mistake there, didn't I? You guys not paying attention to me there. Can't let me get away with this stuff. That's equal to, oops. That's equal to, the mean of the first group is 1.8. The mean of the second group is 3.4. And the mean of the third group is equal to 4.4. So I'm going to find the overall difference between these means. Okay, so the differences are, it's in both places here, so I don't have to do it. The differences are equal to 3.2 minus 1.8 Okay, and I'm going to copy that down. So the difference there is 1.4. Okay, there's my 1.4. Now I'm going to square that difference, just as I did before. Some of them are positive, some are negative. And I'm going to fill down. Okay, now, next what I'm going to do is I'm going to take each one of these squares of the differences, right? And I'm going to say, well, you know, I have to make up for the fact that that really represents the number, also represents number of values. I was in luck here that the sample size was the same for each one of them. I'm accommodating that now by this problem here, I think, right? What happened here? Equals, it didn't copy down right, okay. Equals, okay, and I'm gonna multiply by the sample size for each one of these to get our total. So it's going to be equal to. Okay, hang on a second. Something went wrong here. Is that a negative number? Let me just check this. Equals. Nope, that should be okay. I'm not sure why I'm getting a negative number there. There we go. That's better. Okay, so I wind up with the sum of the squares of the differences between the means being 17.2. That's the sum of the squares of the differences between the means. Okay, so the sum of the squares of the differences between the means, I'm going to put that down here. That's equal to 17.2. Now, what are the number of degrees of freedom between the groups? So it's the number of groups minus 1. So we got 3 groups. I'm not sure why that didn't work. I don't know if I clicked into the wrong box, but we got it right this time. So we're doing basically the same thing we did here with the 3 means for the groups as we did for the variability within the groups. Okay, and we found that the sum of the squares of the differences for those means, if they had, if those means were, if every value in there was the same value, which is the value of the mean of each group, the sum of the squares of the differences between those means would be 17.2. But now we have to divide that by the number of degrees of freedom between the means. There's 3 groups, right? So degrees of freedom are 3 minus 1, number of groups minus 1. So that's 2. So the average or mean sum of squares between the means is equal to 17.2 divided by 2. And that's equal to 8.6. So the mean sum of squares between the groups, between the means of the groups, is going to be equal to 8.6. Okay, so now after we go through this torturous calculation, finally our F-score is going to be 8.6 over 2.1. I just want to point out the fact that the further apart the means are, the bigger would have been our difference in the sum of squares, the bigger the top part of this equation would have been. The further apart the means are, the bigger this number becomes. The bigger this number becomes, the bigger the F-score becomes. And if we look at the variability within the groups, the smaller the variability, the narrower the groups, the closer the numbers in the groups are together, the smaller this number becomes, right? So the smaller this number becomes, the bigger the F becomes also, because the denominator gets smaller, the value of F increases. So this F-score is doing everything we want. We want to see a situation where the means are far apart, but the distributions are skinny, are narrow. And that's exactly what this formula is going to give us, a situation where we can predict whether or not they're far enough apart, and if the variability is small enough that we can say that there are groups in here that are differences. Did you calculate the last column, the differences squared? How did you count? Differences squared, I just multiplied by, that's actually the sum of the differences squared. Remember, there were 15 values here, but it's only represented by this one number. So I multiply by 5. So it's 1.96 times 5 to get 9.8 to account for the fact that these numbers actually represent the 5 numbers that are in this distribution, that mean. So I'm multiplying by 5, and then I'm dividing by the number of degrees of freedom. I did that for each group. Now, had there been 7 people in this group and 6 people in this group and 3 people in this group, well, then it would have been 7, 5, and whatever, 3, whatever it does. So yes, it's kind of a weighted average. Exactly. Exactly right. It accounts for the sample size. Okay, so now what is F equal to? F is equal to 8.6 divided by 2.1. So now, the further apart the means are of the 3 groups, the narrower the groups are, the less variable that the groups are, the bigger this number becomes. So now we have to say to ourselves, is this number big enough for us to reject our null hypothesis? Let's talk about that now. It's a little late, right, to talk about null hypothesis, but now that we see how this calculation is done, maybe it's a good time to discuss it at this point. So our null hypothesis is going to be that the mean for Alice is equal to the mean for Jim is equal to the mean for Fred. They got them out of order there, but you get the idea. Order doesn't make any difference. And the alternative hypothesis is going to be that at least 2 of these means for the population means are different. Don't have to be all of them, just at least 2 of them are different. Okay? In other words, this is not true. We can reject the null hypothesis if that's not true. That doesn't mean that the mean for Alice has to be equal to the mean for Jim, has to be not equal to Jim and not equal to Fred. It could be Fred is not equal to Alice, but I can't prove the rest of it, right? Doesn't matter at this stage. Right now, we're just looking at this hypothesis, that they're all equal, or there's at least 2 of them that are different. Okay, so now we came out with an F score of 4. And we know that based on how this is calculated, the bigger that number is, the less likely we'd be wrong if we reject the null hypothesis. The less likely that all 3 of these population means are the same. So the bigger the number is, the more confidence that we have that we can reject the null hypothesis. The smaller our p-value, our probability of being wrong. Okay, and if it's less than 5% our probability of being wrong, we would reject our null hypothesis. However, a lot of times when we get a number like this, and we're doing this by hand, right? Well, it's going to be difficult for us to calculate a p-value, but we can go to a table and look up what? What kind of value do you think we're going to be looking up? F, what would I call it? F, the value of F that I need to exceed to reject the null hypothesis. Right, bingo, right? The stuff is really all the same stuff, right? Just repackaged. Critical value. Okay, we need to know what the critical value is for this test. Okay, so now I'm going to go and find my ANOVA table. I hope I'll find it. See if I can't find it here. Here we go. Okay, and this table should at least look a little familiar because it came up before in the lecture portion in Levi's lecture. Okay, and what we're looking for is the area in this part of the curve. And I see 2 degrees of freedom. I see a big one, and I see a little one in this direction. Well, the degrees of freedom that we're looking at in the columns is the degree, this whole table is only for the right tail probability of 0.05. In other words, you want F to be so big that it's past 5% chance that 5%, less than a 5% chance that it would be that big and still be part of this distribution. So we want it far out enough that that area is less than 0.05. This is a one-tailed test. That's all you need because you're only looking for a bigger number. Okay, so we want F to be further out than this. Okay, so now we have two different degrees of freedom. The one on the top, going across the top, is the number of degrees of freedom between the means. So in this case, we're dealing with 2 degrees of freedom. It's 3 groups, we're dealing with 2 degrees of freedom. And the column going down is the number of degrees of freedom within the groups. And we had 15 values within the group and 3 groups. 15 minus 3 was 12. So we're looking for 12 degrees of freedom, and we're looking for 2 degrees of freedom here. So our critical value for this analysis, based on 3 groups, 2 degrees of freedom, and 15 values total in 3 groups, 12 degrees of freedom, is 3.89. So our critical value is equal to 3.89. Okay, our calculated F-score exceeds our critical value of T. In other words, our actual F-score is out past the point where it would be 5%. So the probability of getting that value, if the null hypothesis is true, is going to be smaller than that 5% that we would have gotten at exactly 3.89. So what do? Do I accept my null hypothesis, or do I reject my null hypothesis? Opinions. Right, we reject it. We exceeded the critical value of F and we reject our null hypothesis. Exactly right. Couldn't be simpler. Well, it could be simpler, but it's reasonable. Now, we reject our null hypothesis that this is true. Do we at this stage know which of these groups are different from one another? We only know that at least 2 of the groups are different from one another. We don't know. I'm going to take a wild guess and say that Fred is different from, what is this? This is Alice. Fred is different from an Alice because the means are furthest apart, right? That would be a reasonable guess, but you could get fooled because the variabilities of compared to these 2, the variables could be very wide and the variability of Jim could be very narrow, and maybe it doesn't come out that way. You could get really kind of fooled on this. So this analysis only tells us that we can reject this null hypothesis that all the means are different. However, now we have to do another test to determine which of the means are different and what the probability of their being different are. Okay, so now we're not going to do that manually. That's going to be a relatively complicated calculation, and there's several different methods of doing it. We're not going to do that manually. We're going to use SPSS to do that. And I'm about to take the same data and look at it in SPSS, but I want you to remember some interesting numbers. 8.6 was the mean sum of squares between the means. 2.1 is mean sum of squares within. The degrees of freedom were 12 and 2, and our F-score was 4.09. Okay, so question was, will we have to create a chart like this on the exam? I don't think I would ask you to do this manually on the exam. I might ask you to do it in SPSS. We're about to see how much simpler that process is. So I have an SPSS file, which is already set up, which is exactly the same data. Okay, I'm going to open this up. I won't ask you to import this from Excel. If I ask you to do this, it will be with a data set that's already in SPSS format. So I'm going to open this up. Okay, SPSS will start up. Eventually, it'll start up. If the spinning ball goes away, there we go. Okay, we're coming. Okay, and as usual, for some reason, it opens up twice, but that's okay. So here's our data. Our data is organized in a slightly different way. We have a variable which represents the group, right? Could have been A, B, and C, Fred, Jim, and Alice in this case, or the borough, Bronx, and so on and so forth. If I turn off, this is actually, I look at the variable view, I can see that, well, the group, 1 represents Fred, 2 represents Jim, 3 represents Alice, right? That group is the variable. It's a nominal variable. The measurement, I should change this, is a scalar measurement, is a number, right? SPSS got fooled when I opened that up because if you look at the numbers, they look almost like they're groups, right? Like five groups, almost like Fred and Jim and so on and so forth. But they are scalar variables. Okay, so at any rate, now I'm going to go ahead and I'm gonna do what I need to do with this, just to show you, just as a warm up, not something you might necessarily have to do. I'm going to go into descriptive statistics and explore. And I'm going to tell it, give me the measurement, whatever this represents, and factor it by group, right? In other words, give me all the statistics for Fred and Jim and Alice, mean, standard deviation, all that kind of stuff. And you know what? Give me also displays of the plots and so on and so forth. Why don't you give me a histogram while you're at it, okay? So we know it's going to do a box plot automatically. So let's see what we get. So SPSS analyzes this for us. It says, okay, there's 5 values for each one of these groups, so on and so forth. It finds the mean for Fred is 1.8, the mean for Jim is 3.4, the mean for Alice is 4.4. Familiar numbers, right? Same thing we got. Okay, it finds a standard deviation, gives us a histogram. Now, one of the caveats, one of the assumptions here is that these three groups are normally distributed. The populations that they're drawn from are normally distributed. You wouldn't be able to tell that from these small. Yeah, exactly. I agree. Thank God for SPSS. What do you see? Okay, so you can't tell that from these little tiny groups, but that's one of the assumptions. One of the things you might want to review for the test, or at least have handy, is that if we're talking about confidence intervals proportions, confidence intervals of this, how to do a t-test, and so on. If you look back on the PowerPoints, you'll notice that wherever applicable, you might see a mention of the assumptions that go along with that test. In other words, does the population have to be normally distributed? Does it have to be an independent sample? Does it have to be a random sample? You know, that kind of thing. Okay, one of the assumptions for this is that it is a randomly selected independent, and that they are normally distributed, each one of these three groups, the populations at least anyway, not necessarily these samples. And it assumes heteroskedasticity. Heteroskedasticity. Anybody hear that term before? Heteroskedasticity as opposed to homoskedasticity. Okay, we're going to talk about that when we come back out of this. I'll just mention what those words mean. Okay, so at any rate, so it did the basic analysis for us. And look, it even did the box plots for us. And we can see there's quite a bit of difference between Fred and Alice. Here's where the medians are. And we can see Alice is much more variable than these other guys are. So that doesn't help us. Variability is not a good thing for us, right? We don't like variability when we're trying to compare these, because the variability is what the narrowness of the spread here helps us, right? The distance apart of these medians helps, but the variability being narrow also helps. Okay, so we got an idea what this data looks like. Now let's go ahead and do our analysis. Analyze. What are we doing? We're comparing means. So we compare means. We're going to go here. Compare means. It's not a one-sample t-test, not independent, not paired. It's a one-way analysis of variance. Don't worry about for the moment what we mean by one way, but it's an analysis of variance. Single variable, basically. I'm going to do the same thing. I'm going to put the measurement into the dependence list. That's what it's going to calculate our mean. And I'm going to put the groups into the factor. We want it broken up into these different groups. So now, I'm not going to change anything here for the moment. I'm just going to go ahead and I could have asked it to do our descriptives right here, but I did it as a separate exercise there. Okay, I'm not going to bother with it. I'm just going to leave all of the defaults on, and I'm going to click OK. Okay, it's going to calculate that F score. It's going to do the same thing that we did. It's going to calculate the variability within the groups, variability between the means. It's going to divide by the degrees of freedom, and so on and so forth. Let's take a look at this. Between the groups, sum of squares 17.2. Within the groups, 25.2. Degrees of freedom 2. Divide 17.2 by 2. We get the 8.6. The top part of our fraction. Within the groups, the sum of squares was equal to 25.2. The mean sum of squares was equal to the sum of squares was equal to 25.2. divided by the number of degrees of freedom, it becomes the mean of the sum of squares, which is that into that it becomes out 2.1, same thing that we got. And the F statistic comes out to be 4.095. We got 4.094, but if you remember, it was even 4.09456 something, right? So actually, if you round it up, it's that number. SPSS, in a moment, did that entire calculation for us. Not only did it do that, but it has a built-in calculator for the F statistic. And instead of having to rely on whether or not we exceeded the critical value, it actually tells you what the probability of getting this large an F score is for this particular situation. And it tells us that our probability of getting this score, if there's none of these groups are different, is 4.4%, 0.044. Well, as in most calculations, as in this one, our alpha error, acceptable level error, is 5%. So since our p-value, notice they use significance for p-value, since our p-value is less than 5%, we can reject the null hypothesis. Okay, and since we reject the null hypothesis, we accept the alternative hypothesis that at least one of these pairs was different. Prior to the ANOVA, prior to the analysis of variance, I did the. Prior to the analysis of variance, I did the what do you call it? The descriptive statistics. Descriptives, explore. Right? They're still there, and I clicked OK, and it gave me the means and the medians, all that kind of stuff. Okay, it didn't really need to do that to do this calculation, but sometimes it's nice to get an idea of what your data looks like. Is that where you're driving at, Jonathan? Is that what we were talking about? Okay, all right. So they got same result we did. Now SPSS allows this to take us one step further. We've rejected the null hypothesis that all of these the means for all of these three populations are the same, but we haven't proved yet which ones are different. We don't know which ones are different from one another. So we need to do an additional test, a test in addition to after the fact of this being done. Another way of saying after the fact in Latin is post hoc. So I'm going to go back to analyze, compare means, analysis of variance, exactly the same spot we were before. And you may notice that there's a button there called post hoc, after the fact in Latin. I'm going to click on that. Post hoc allows me to do an additional test after we're done and have shown that there is a difference. We can do an additional test. Will actually point out for us which of these compared means are different, whether group A and group B are different, group B and group C, group A and group C, and so on. There's a number of these. This is least squares, this is Bonferroni, this is Tukey. The couple of most popular ones are this Bonferroni and this Tukey. There's a method behind each one of them that each one of them use. We're not going to go into that. You can choose. We'll either tell you to choose one of these, which one to choose, or probably if I were you, I would use Bonferroni or Tukey. We're going to use Tukey. Okay, and that's the name of the person that developed this test. This actually stands for least squares. Okay, so let's use Tukey. Use that method. I believe Tukey is a relatively conservative method. Well, I'll tell you what. We'll do Bonferroni next. See if we get more encouraging results. How you got into post? Okay, yep, no problem. I can go back again. Analyze, compare means, one-way analysis of variance. Okay, now before we were in this situation, I'm going to move the measurement, what I'm finding the means of, those numbers I'm finding the means, I'm going to move that into the dependence list. Excuse me. And I'm going to move the groups, Jim, Alice, Fred, Bronx, Brooklyn, Queens, etc. So I'm going to move that into the factors. Then we're finding the means for the groups separated from each other, not just that whole list of data. Now, to get the post hoc test, I just click on there and I check off which post hoc test I want to do, or post hoc tests if you want. Okay, I'm going to click continue, and then I'm going to click OK. It's going to repeat the calculation we just did since I told it to. And in addition to the calculation that we did before, Same result, 4.095. Significant that's less than 0.05, so reject the null hypothesis. Now it actually shows us the results for each individual pair of groups, each individual mean. So if we compare Fred and Jim, the probability of being able to reject the null hypothesis that they're the same mean is a significance, a p-value of 0.22. Can we reject that null hypothesis? No, we need that to be less than 0.05. How about Fred versus Alice? Fred versus Alice is 0.037. In other words, if we reject the null hypothesis that the mean for Fred and the mean for Alice, the populations that they represent, are the same, if we reject that and say that they're different, our chance of being wrong is 3.7%, which is less than 5%. So we can say that Fred and Alice are not the same. We reject that null hypothesis. Okay, let's try Jim. Jim and Fred? Nope, don't work. Jim and Alice? Nope, don't work. Right? So the only pairs of means for these populations that we can say are different are Fred and Alice. And you may notice that SPSS does this a lot. It repeats the test again, Alice and Fred and Jim, Alice and Jim, and so on. So we already know that Fred and Alice is 0.037. If we see it Alice and Fred, it's just a repeat of the same test, gives you the same result. I'm not sure why they bother to, give us this grid this way instead of just giving the result one time. But I guess it's that they use their judgment. That might be the best way to do it. And in fact, not only does it do that, but let me see here. Let me see if I can actually see it here. Okay, the mean difference is significant. It even tells us the mean difference is significant at 0.05. And there's an asterisk right there. The mean difference, they actually asterisk the values, 2.6 minus 2. Mean difference between them. They asterisk the Alice and Freds here to let you know that don't miss this one because this one's significant. Okay, not that hard, right? Let's try Bonferroni. Let's just for the hell of it. Analyze, compare means, one-way analysis of variance, and except this time I'm going to do Bonferroni. I'll do both. See how they come out. Okay, let's try it. See if we get the same value. Jim and Alice don't work. Well, that's a good question. That's an excellent question. Jim and Alice are greater than 5%, right? In other words, it's greater than 5% chance of being wrong. So we don't say that if we say they're different, if we reject the null hypothesis, that they're the same, right? Okay. In other words, either the means are not far enough apart for Jim and Alice, or the variability for Jim and Alice when compared to each other is too great and they overlap. Maybe the means are far apart, but there's so much variability we can't tell for sure because the numbers within them are so scattered, right? That's the whole point of this analysis of variance, right? We want the means to be far apart, and we want the variability within each of the groups to be small so that we can see easily, just like with those trees, we can see easily that they're different trees and not just one big tree. And let's see, Bonferroni. Okay, here we go. Here, let's see the level of significance that we have for Fred and Alice if we use Tukey, 0.37. And what about if we use Bonferroni? We get 0.045. In other words, we got closer to failing to reject with Bonferroni. That would suggest to me that all of these numbers are bigger for Bonferroni. That would suggest to me that Bonferroni is a more rigorous test. In other words, it makes it harder for you to reject the null hypothesis, which is nice if you don't want to be wrong and reject the null hypothesis unnecessarily. We don't like alpha errors, right? Those are alpha errors. We don't like those, right? Of course, there's more of a possibility of a beta error here because if this were just a little bit bigger, we would have failed to reject the null hypothesis that Fred and Alice are different, and maybe they really are, right? So this increases our chances of beta error, but it reduces our chances of an alpha error, rejecting when we don't have justified rejecting. Okay, Tukey is a little bit more liberal. It decided that, I'm pretty sure we can reject that. It's easier to reject a null hypothesis than it is with Bonferroni. Okay, so there's a variety of reasons you would choose one over the other, but actually, how rigorous the test is, it's, I guess that's conceivably one of the reasons why you might check one versus the other. Okay, you might have also seen that it means that mean difference is significant. Da, da, da. Okay, and I think it said something in one of these about assuming that the variability, the variance in each of the three groups is different. That's heteroscedasticity. This test assumes different, the math is based on different variability in each of the three groups. We don't try and prove the variability in the three groups and assume that they're all the same. Okay, homoscedasticity means that you want the variance in the groups to be the same instead of different. So homoscedasticity means the variability within the group, standard deviation of variabilities within the groups are the same. Heteroscedasticity means that the variability within the groups is different. Okay, so that's what this test assumes, that they're different, and works from there. Okay, so not that bad, right? Not that terrible. And what does this do for us? This allows us to take any date. Let me see if I can't find something real quickly. Another example, NC birth, right? We got this one in here. It's a handy one. I'm going to look for something in here that involves, remember, this only works with numerical variables and nominal variables, right? You want groups. The nominal variables represent the groups, and the oops, that's a Word document. That's not SPSS. Let's see. NC birth. That's okay. I want, oops, I've got something in front of there. .sav. Yeah. Here we go. I got so many copies of this thing. God, if you can find it. We rely on this quite a bit because, oh no, I don't want the text version of it. I want the actual version. .sav. This should be. Okay, let's try that one. Oh, there we go. Okay, let's take a look at this. Now let's take a look at, so we got something that's got more than one, a nominal variable, categorical variable. Well, sex of the infant is going to be, it's only going to be two categories. We would use a t-test on that. Okay, how about marital status, married, not married? No, that's only two variables. How about the race of the mother? Well, the race of the mother, yeah, it looks like there's more than two variables there. I think, right? I think there probably is. How about anything else here that's more than two variables? The ethnicity of the mother. Let's see. I think that's reduced to. Let's try the race of the mother. We'll give that a try. See if there's more. I think there's more than two variables there. I'm going to do some descriptive statistics first. Explore. And I'm going to look at the weight of the child, birth weight of the child. Okay, and I'm going to take the race of the mother as my factor list. And I'm just going to look at the basic statistics. See what I get. Okay, so I have race of the mother, white, black, American Indian, Chinese, Pacific Islander, or Asian or Pacific Islander. Okay, so I have 1, 2, 3, was it 4? 1, 2, 3, 4, 5 groups there. Okay, let's say I want to compare the means for these 5 groups. I want to do an analysis of variance. I want to compare the means for all 5 of these groups. So I'm going to say analyze, just compare means, one-way analysis of variance. I'm going to move the weight of the child into the dependence list. That's actually what I'm calculating the mean of, and the race of the mother into the factor list. And I'm going to say okay. I'm not going to hit post hoc yet because I want. Now we got our. We can see that there's differences here. This one, look at the differences in variability. Very big difference between the sample sizes here as well. That says, no. And look, they look kind of normally distributed, right? That helps, right? Which is kind of what I would have expected. Okay, so now this is what we got. Let's see what our F score comes out to be. Well, take a look at this. Our F score comes out to be 5.8, right? And our P now, what's our critical value? Our critical value is not what it was before. Our critical value is different because critical value is based on the degrees of freedom. Okay, there were actually must have been 6 groups. Okay, it's six minus 1, which is 5 groups, and there must have been, I guess, 798, 95 people in this group that we actually had numbers for. There might have been some missing values. So that would have been the 795 minus the 5 for each group, 1 for each group. Okay, and so that degrees of freedom 794. So we would have had to go look on our table for whatever numbers would be closest to the 5th column across and almost all the way down to the bottom on the rows. Okay, and that would have given us our critical F value, whatever it's going to be. Let's say it's 3 or 3.5 or something like that. We would have compared the F score against that to see if we exceeded that critical value. Well, SPSS doesn't require it to do this. It tells us right off the bat that the probability of being wrong, if you reject the null hypothesis, that the means for all of these groups is the same, right? Well, the probability of you being wrong is less than 1/10 of 1%, right? Less than 0.001. Okay, which is less than 0.05, which means we can reject that null hypothesis. Now, of course, if we want to know which groups are different, we have to go to analyze. We have to repeat the analysis, compare means. So this time we're going to turn on post hoc tests. Okay, and I'm going to use Bonferroni because that's more conservative. I'm going to click OK. I don't like making alpha errors. Oops, I got a problem there. Not performed as at least one group. You know what happened here? One group have fewer than 2 cases. So you can't calculate the degrees of freedom for that group because fewer than 2 cases, 1 minus 1 is 0, and you can't divide by 0. So it couldn't do that. I need to eliminate, the Filipino person. Okay, I'm going to go here. So there was one Filipino person that was a different group. Okay, for whatever reason. Let's see. Let me see if I can't find them. Let me see if I can't. Okay. Let me sort the cases. Sort the cases by race of the mother. And I'm going to say OK. Okay, the output table comes up. Is it done? Did it do it? Looks like it did it. So we need to work our way backwards down to the, oops, went too far. Okay. Oh, must have been in here somewhere. Boy, I don't see them. Where are they? American Indian, Chinese, American Indian. Here's that person. I'm going to take that person. I'm going to delete them. Okay, I'm going to repeat the analysis. Analyze, compare means, one-way analysis of variance. Everything's all set up here. Even the post hoc test still set up. I'm going to click OK. This time, hopefully it'll work. And indeed it worked this time. It gave us a table. All we're interested in now is which of these significants are less than 5% and which are asterisk, right? Because that's going to tell us that the difference, that we have enough evidence to say that the mean weight of children born to white mothers in this study is different than the mean weight of children born to black mothers in this study. We can't say for sure about any of these others. This is just a repeat, black versus white. Again, same result. Oh, wait a second, I'm wrong. We can say that there's also a difference between black infants and Chinese, Asian, or Pacific Islander. And let's see if we can see any others. No. Those are the only ones that are significant, right? Those 3 comparisons. So we would be just looking for which of these are below 0.05. Okay, so Or if you could imagine with 800 subjects here, what this would have been like to calculate if we had to do it in Excel or with a calculator, it would have been mind boggling. We'd be spending days here. And trust me, I remember those days, and you did spend hours and hours, doing these kind of calculations, literally by hand. When you didn't have computers to do this stuff, or when you didn't have computers that were not personal computers available. I mean, for a long time, there's been even not as old as I am, there have been mainframe computers that have been available, but they're usually in a situation, an academic situation, a business situation, where relatively few people have access to them. So most people would still be cranking the numbers by hand. So you can imagine we save a lot of time here. And of course, if you want to, let's say you're working on a project and you're comparing 5 groups like this. One of the things that you might want to do is your include the box plot that came with this to describe your data, to include the histograms to show that they are the populations or the samples suggest that the populations are relatively normal. And then you might want to include that table, copy and paste that table into your poster to demonstrate that. Or copy and paste this table with your results to demonstrate when you found significant differences, which group you found significant differences in. In other words, you found the F score and significance that justified doing your post hoc test, and your post hoc test demonstrated which of these were actually different. Okay, so I think that's really